Okay, good morning everyone. So here is my next lecture on digital communication with having a code KEC 601, and the lecture is based on modulation techniques, which is basically ASK and BPSK techniques. So in the last lecture we have discussed about different types of techniques based on pulse shaping, and there we have discussed about Nyquist criteria for zero ISI and zero forcing equalizer and all. So in this lecture I am going, because it's a special lecture, I am going to discuss about two techniques, which is amplitude shift keying and binary phase shift keying. So we'll go through all the details of these two techniques, modulation and demodulation diagrams and equations of all these techniques. So before going into the modulation techniques, we want to know about what is communication. So basically main purpose of communication is to transfer information from a source to a recipient via channel or a medium. So in any communication system, either it can be analog or a digital one, we require three important blocks, which is source or the transmitter, the channel and the receiver. So in between we require modulation and demodulation also, and different types of coding techniques also, you can say, like source coding or channel coding. Source coding after the transmitter and channel coding is after the source coding. So we have a sequence of coding before passing all the signal or the demodulated signal into a channel. The channel can be both type of wired or wireless, or you can say the wired channel like coaxial cable and optical fiber, and a wireless channel like free space optics or a microwave link. So in the source we have any type of source we can use, either it can be audio signal or a video signal or a text signal. With the help of a transducer, we can convert these signals into an electrical format. The channel, before the passing to the channel, we can use source coding and channel coding, and then after the channel we have a receiver and a recipient. So in the receiver also we have demodulation process, then we have channel decoding process, and then we have source decoding process, and then we will get our actual data which we have transmitted. So next we can discuss briefly about all these blocks. The first one is the source block, which can be analog or digital. The transmitter or the transducer or amplifier. So the transmitter can be any type of transducer, amplifier, modulator or oscillator, or power amplifier or antenna. A channel, which I have already discussed, that is coaxial cable, optical fiber or free space. A receiver can be an antenna, amplifier, demodulator or oscillator, or a power amplifier or a transducer again. And the recipient is basically a loudspeaker or a person or a computer, so where we have received all these signals. So next type of information is voice, data, video, music, email, etc. type of communication system. We can use different type of communication system like public switch, telephone network, voice, fax, modem, satellite systems, radio, TV, broadcasting, cellular phones, computer networks, LAN, WAN or WLANs. These type of communication systems we can use in this communication process. So why we are going into a particular technique which is digital? We can use also analog technique, but there is a lot of advantages of using digital techniques over analog techniques. So digital techniques need to distinguish between discrete symbols allowing regeneration versus amplification. Good processing speed also there, and there are a lot of different methods, as I have told you, like a source coding method or a channel coding method. That's why digital is more advantageous as compared to analog. In analog techniques, there are no such kind of thing, that is source coding or channel coding. So basically source coding is a technique of data compression, where we compress the data into minimum number of bits, and in channel coding there is possibility of data detection or the error detection on correction. Then we have equalization technique in digital, like zero forcing equalization or equalizers. Then there are security things are also available in digital, like scrambling, where we can encrypt data or decrypt data according to our need. Then it is easy to mix signals and data using digital techniques. Multiplexing techniques can be used using all these digital techniques, which is not possible in analog techniques. So here is a diagram showing the original pulse signal, distance some signal, then degraded signal, then signal is badly degraded, amplification to regenerate pulse. So this diagram basically shows how the data is transmitted from one point to another point. It is degraded in the channel basically, and then it is amplified and regenerated so that we can get our actual data. So basic digital communication transformations are formatting source coding, transform source into digital symbols, which is called as digitization, selects compatible waveforms, matching functions, introduce redundancy in the case of the channel coding. Despite there are some errors which can be introduced in the data at the channel, but we can introduce some redundancy, redundant bits or parity bits so that we can easily recover our original data. So it is essential for digital communication. What are essential points are modulation and demodulation. Modulation is basically the process of overlapping or modifying the information or the carrier signal as accordance with the modulating signal. Demodulation reverses the process of modulation. It involves detection and retrieval of the original information signal. So there are some types. In the demodulation process, we can use coherent detection process, wherever the in the coherent detection process, the carrier waveform which we have used at the transmitter, we have to use the same carrier at the receiver. There are some non-coherent processes also there, where we don't require the same carrier to be at the receiver, and it does not require the phase information matched at the receiver. And the categories like coding, decoding. So here we have waveform coding, we have structured sequences, involves the use of redundant bits to determine the occurrence of errors. Multiplexing multiple access is also synonymous with resource sharing with other users. We can use frequency division multiplexing or time division multiplexing or code division multiplexing in the case of the digital communication as compared to analog. So why digital communication is much important? Can combine different signal types like data, voice, text, etc. Data communication in computers is digital in nature, whereas voice communication between people is analog in nature. The two types of communications are difficult to combine over the same medium in the analog domain. So using digital techniques, it is possible to combine both the formats. Either it can be a voice format or a video format or a voice combination or a data combination, and they can be easily transmitted through a common medium. There are a lot of encryption and decryption techniques available in the digital communication also. So now coming to the main part of this lecture, that is modulation techniques. So we have, before going into the modulation techniques, we must know about what is passband signal and what is baseband signal. So baseband signals are basically your digital data which you are giving into the modulator. So digital data which is modulating signal or baseband signal is converted into passband signal with the help of these modulation techniques. So we have a different type of modulation techniques, but necessarily or primarily we have three modulation techniques, but which is amplitude shift keying, phase shift keying and frequency shift keying. The keying word here is basically switching. In analog communication, we learn about modulation technique or modulation like analog amplitude modulation or phase modulation or frequency modulation. Here the term is something like different, that is amplitude shift keying, phase shift keying and frequency shift keying. As we have the data which is switched between 0 to 1 or 1 to 0, that's why it is called as switching or it is called as keying techniques. So the receivers are here for all these techniques are the same, that is coherent detection technique we can use here. The receiver is synchronized to the transmitter with respect to carrier phases. So we have to see here, look into the thing, that is the carrier of the transmitter and the receiver should be same. That is the phase or the frequency or the state of polarization of the carrier must be same for both the transmitter and the receiver. If you are going into the non-coherent techniques, there is no such requirement of the coherent carriers like the same phase or the same frequency or the same state of polarization for the carriers. So there are some preliminaries which we can discuss here. Given a binary source, the modulation process involves switching or keying the amplitude, phase or frequency of a sinusoidal carrier between a pair of possible values in accordance with the symbols zeros and ones. So if we in the case of the analog communication, we have two signals, that is message signal which is empty and the carrier signal which is CT, which is A, C or A cos omega naught t, or we can also write A C cos 2 pi FCT plus phi, where phi is your phase. So in the analog case, this message signal is also analog. This is also analog. But in the case of the digital, if we go through digital techniques, this message signal MT is now your data, which is BT or the sequence. So all of them are examples of the band pass process, binary shift keying or amplitude shift keying, or you have binary phase shift keying, or we have binary frequency shift keying. If the carrier amplitude is keyed between two possible values used to represent symbols zeros and ones, so it is called as binary shift keying, amplitude shift keying. So here the carrier amplitude is going to vary as accordance with the modulating signal. Similarly, the carrier phase is keyed between the two possible values used to represent symbols zeros and 1. So here the phases of the carrier has to be vary according to the message signal or the modulating signal, and there are two possible phases, that is 0 degree or 180 degree, because it's a binary phase shift keying technique. Next is the binary frequency shift keying technique. The carrier frequency is keyed between two possible values used to represent symbols zeros and 1. So here there are two frequencies, high frequency and low frequency. So here it is FH and FL. One is high frequency and other one is the low frequency. So for data bit 1 it is high frequency, for data bit 0 it is low frequency. In BPSK we have two phases, 0 degree and pi. So for bit 1 it is 0 degree, or bit 0 it is 0 degree. You can take it is as vice versa, and pi for bit 1. We will go through all these techniques one by one, and we will go through the modulation and demodulation process, and then equations of these techniques. Decreasing the bit duration TB has the effect of increasing the transmission bandwidth. So if you decrease the bit duration, that is TB, so only the disadvantage is that the transmission bandwidth required is much more. So in that case we have to see about how the bit duration has to be increased. So there are a lot of different modulation technique like QPSK, quadrature phase shift keying, where we take the symbols like 0 0, 0 1, 1 0 and 1 1. Here the bit duration is 2 TB, not TB. So obviously whenever the bit duration is increased, the bandwidth requirement is less. So difference that distinguish digital modulation from analog modulation: the transmission bandwidth requirement of BFSK is greater than that of BASK. Obviously BFSK has a bandwidth around 4 FB and ASK has a bandwidth of around FB. So however the same does not hold for BPSK. For BPSK the bandwidth is around 2 FB and it is around FB. So in case of BPSK we have lesser difference between BPSK and ASK as compared to BFSK and ASK. So now coming to binary amplitude shift keying, we will also call it as on-off signaling or on-off signaling, on-off keying also. So this is also termed as on-off keying, because for bit 1 there is some carrier and for bit 0 there is no carrier. So if we see the equations here, so BT, which is your actual bit or the output for the bit 1, that is for symbol 1 it is under root EB, and for symbol 0 it is 0, or in case of equation you can see that is under root 2 EB by TB cos 2 pi FCT for symbol 1 and 0 for symbol 0. So the average transmitted energy is EB by 2. These equations we can, because in ASK it's a simple multiplication of the carrier with the binary data. So whenever the binary data is 1, the carrier is present. Whenever the binary data is 0, no carrier is present. So we will get ST is equivalent to AC cos 2 pi F naught T, or for bit 1 and 0 for bit 0. Or we can take the power of this signal, that is PS, which is AC square by 2, or we can write it AC square is equivalent to 2 PS, or AC is equivalent to under root 2 PS. So we can change the equation ST, that is under root 2 PS cos omega naught T for bit 1, or we can also change it like this, under root 2 power is energy per unit time, under root 2 EV by TV cos omega naught t. So this is your ST for bit 1. So similarly for symbol 0 or for bit 0, it is 0. So we have this kind of technique which gives you the carrier only at the bit position at the bit 1, and we have no values of the carrier at bit 0. So if we go through the generation and detection of ASK signal, generation of ASK signal are simple because we use a product modulator. In the product modulator, we will give one input as a data or the data stream, which is a pattern of ones and zeros, and this data is to be converted into NRZ-L form or unipolar NRZ, which is called as unipolar non-return to 0. So what is non-return to 0? Non-return to 0 means if we have pattern 10110 and every bit has a bit duration of TB. So for non-return to 0, it has plus A for bit 1. Again, because it's a unipolar, for 0 it is 0, for 1 it is again plus A, then for 1 it is again plus A, for 0 it is 0. So it's for whole duration, that is TB. So for non-return to 0, it is for whole duration, that is TB, which is the bit duration. Sinusoidal carrier we have used here under root 2 by TB cos 2 pi FCT, and this sinusoidal carrier under root 2 by TB cos 2 pi FCT is also a basis function which is phi. So this can also be represented as phi. So if we want to have a constellation diagram or signal space representation of this ASK signal, we must know about the phi or the basis function or the orthonormal signal. So in terms of orthonormal signal, we can represent our actual signal. Then detection of ASK signal, it's the simplest way is to use envelope detector exploiting the non-constant envelope property of the BPSK signal. So in the detection process, we require a low pass filter, comparator circuit, and in the comparator circuit we have to give some threshold value, and with the threshold value it will compare the input and the output and then give accordingly our bits. So if you see the waveform of the ASK signal, we have taken here a sequence, binary sequence 0011 011 001, and according to this binary sequence we have created here three types of signals here. That is, the first one is the ASK signal. So in ASK signal, wherever the carrier is present means that is the bit 1 multiplied with the carrier. So wherever the bit data or the input sequence is 0, there is no carrier present. So here there is no carrier. This is carrier. So wherever the data is 0, there is no carrier. Wherever the data is 1, there is carrier. In the case of the FSK or the frequency shift keying, we have low frequency and the high frequency. So wherever the data bit is 1, the frequency is higher. Wherever the data bit is 0, the frequency is lower. Similarly, in the case of the PSK, we have phase shift keying, and it is basically from whenever there is a transition between 0 to 1 or 1 to 0, there is a phase change of pi degree. So here we can see that the phase change of pi degree will occur. So now coming to BPSK modulator. So in BPSK modulator, as I have told you, a mixer circuit is there or a modulator. In modulator, we have to give a unipolar binary sequence. Then there is a carrier signal, which is your cos, and the data is your, or you can write under root 2 PS, and the data is here dt or pattern bt. So bt under root 2 PS cos omega naught t, we will get our output, or st is equivalent to under root 2 PS cos omega naught t for bit 1, or you can write as like under root 2 EB by TB cos omega naught t for bit 1 and 0 for bit 0. So these two equations are very important, and then we will get our ASK output signal, which is this equation. So these are equations for ASK modulator or modulation. Now the demodulation part of the ASK signal. So in the demodulation process, we have an integrator circuit here. A comparator which has a threshold value here. So the ASK waveform is multiplied to the product modulator. So we have product modulator, which is again a coherent detection technique is used. So the same carrier is used here. Whatever carrier we have used at the transmitter, we can use the same carrier at the receiver. So ASK input signal, which is your root 2ps cos omega naught t, and it is multiplied with cos omega naught t again. So we will get at this point under root 2ps cos square omega naught t. So we can break this under root 2ps cos square omega naught t, which is under root 2ps 1 by 2 plus cos 2 omega naught t by 2. So then this particular thing is passed through the integrator circuit, which integrate, or a low pass filter circuit which integrate from 0 to dB. So whenever you integrate this particular part, you will have only the term which is under root 2ps by 2 into TB. So after integration, because the next part, which is cos 2 omega naught t over the whole cycle 0 to TB, will comes out to be 0. So after the integration, what you will get under root 2ps by 2 multiplied by TB. Then a decision making device is there, or a comparator circuit is there. A threshold lambda is fixed at the decision making device. So whenever this particular data or this equation, that is under root 2ps by 2 into TB, or you can write under root ps by 2 into TB, comes out to be higher as compared to the lambda. So symbol 1 is detected, or if this value comes out to be lower as compared to lambda, then symbol 0 is detected. So this is all about the demodulation and the modulation process of the ASK signal. Now we are coming into the binary phase shift keying method. So in the binary phase shift keying method, the special case of double sideband suppressed carrier we can have in the analog communication technique. It is same as this technique which is called as DSB-SC. So here the pair of signals used to represent symbol 1 and 0. So here we have equations like for bit 1, we have ST is equivalent to AC cos omega CT plus 0 degree. For bit 0 you can write, and for bit 1, what is ST is equivalent to AC cos omega naught or omega C, whatever you want at the value notation, you can write it, that is minus of AC cos omega naught t. So general equation of BPSK signal we can write, that is BT under root 2ps cos omega naught t. So this is the general equation for PSK signal. The value of the BT depends on plus 1 for bit 1 and it is minus 1 for bit 0. So you will get under root 2ps cos omega naught t, and at another level it is minus under root 2ps cos omega naught t. So basically BPSK signal has two levels, one is for bit 1 and one is for bit 0. So according to that we have the change in the equation, that is BT under root 2ps cos omega naught t. And next we can convert, because here we have convert these equation under root 2ps cos omega naught t in terms of under root EB by TB. So we have under root 2 EB by TB cos 2 pi FCT for symbol 1 and minus under root 2 EB by TB for symbol 0. So Again we have the same type of equation, that is bt under root 2 ps cos omega naught t, or we can also write as bt under root 2 eb by tb cos omega naught t. This is the final equation, modulation equation for BPSK signal. So a pair of sinusoidal wave which differ only a relative phase shift of pi radians. Here the transmitted energy per bit EB is constant, equivalently the average transmitted power is also constant. Demodulation of BPSK cannot be performed using envelope detection technique. So here we again use the coherent detection technique, where we have to recover firstly the carrier, and then that carrier has to be used at the synchronous demodulation or at the receiver. So we can go through these demodulation process in the next slides. So generation and coherent detection of the BPSK signal. In the generation, again we have a simple product modulator. So in the product modulator, we have a signal which is BT, and again it is root 2 PS cos omega naught t. So you will get your VBPSK signal, but this BPSK signal depends on the phases 0 degree and pi degree according to the bit which is BT. So a product modulator consists of two components, non-return to 0 level encoder, because BT obviously this data stream is to be non-return to 0, but it's a kind of a polar data. So the input binary data sequence is encoded in polar form with symbols 1 and 0 represented by the constant amplitude levels, that is under root EB and minus under root EB. So product modulator multiplies the level encoded binary wave by the sinusoidal carrier, which is this, that is CT, and we will get amplitude of under root 2 by TB to produce the BPSK signal. So we will have a look of the modulation and demodulation diagram in the later slides. So in the detection process, we have 4 sections. Firstly, we have to regenerate our carrier, then that carrier has to be used at the product modulator or the synchronous demodulation. So for carrier recovery, we have some blocks, that is first block is the square lobe device, the second block is the band pass filter, then there is a block of frequency divider circuit, and then we will get our output which is the same carrier as the transmitted carrier, and then that carrier has to be used at the synchronous demodulation. So at the synchronous demodulation, we have two inputs. One is the carrier recovered from the original transmitted signal, and the other one is the transmitted modulated signal. So we will see here the diagram of the BPSK modulation and demodulation. So in the BPSK modulator diagram, we have BPSK signal, which is a product modulator. At the product modulator, we have BPSK signal, and then under root 2 by TB cos 2 pi FCT. Then we have a low pass filter. Then there is a sampling at time t is equivalent to ITB. Then there is a decision making device or a comparator circuit, again which compare the value lambda with the input, and if the input is higher, then there will be a logic level 1, and if the input is lower than lambda, then there will be logic level 0. So we will see the waveform of the BPSK, that is wherever the transition is there from 1 to 0 or 0 to 1, there is a phase shift of pi degree. So here we can see the phase shift of pi degree, here we can see the phase shift of pi degree, then again phase shift of pi degree, then again phase shift of pi degree. So we will see here a shape of M type or a W type in the BPSK waveform. In the earlier slide, we have discussed about this particular diagram. We can also recover our carrier with these 3 blocks, that is first one is the square law device, then there is a band pass filter, then there is a frequency divider circuit which is divided by 2. So band pass filter is centered at 2f0 or 2 omega naught. So with this, whatever the BPSK signal is coming, VBPSK, which is equivalent to under root 2 ps cos omega naught t multiplied by BT, because BT depends on the value. BT depends on the value, that is +1 for logic 0, and BT is equivalent to -1 for logic 1. So according to this, we can use this equation at the input, and then this equation has to be squared here, then passed with the band pass filter, then frequency divider circuit. So at the output, we will get cos omega naught t plus theta. There must be some change in the phase. So this particular carrier has to be used at the synchronous demodulator, and then at the synchronous demodulator, if we can synchronous demodulator. So this carrier is used at the synchronous demodulator, cos omega naught t plus theta, and at the synchronous demodulator, the another input is your BPSK signal, and then this output is given to integrate and dump circuit, and then we will get our demodulated output, which is your polar data. So we can use this type of block for carrier recovery, and then for synchronous demodulation process. So this is the waveform which we have already discussed about it, and thank you so much. Because we have discussed about ASK and PSK because of the less time, and we can also discuss about FSK also, which is your frequency shift keying, the last technique, which is basically binary frequency shift keying, and there the carrier frequency is converted or varied according to the modulating signal. So wherever the data is 1, the frequency is higher, wherever the data is 0, the frequency is lower. We can also discuss about constellation diagram in these techniques. So if you want to see about the constellation diagram, you have to concentrate on the orthonormal function or the basis function. So with the help of the basis function, we can draw these constellation diagram, and we can find out the distance between the 2 points, that is between the bit 1 and bit 0. If the distance between the 2 points are higher, then the probability of the error or bit error rate, you can say, is minimum. So basically, distance between the 2 points is inversely proportional to probability of error. So we use these constellation diagram or signal space diagram for analyzing our modulation techniques. So whether which modulation technique will give you best results, or which modulation technique have lesser chances of error if you use that technique. So if you compare all these techniques, because we have left with lesser time, and we can compare these techniques, and then we will see which technique is best, or in terms of bandwidth, in terms of distance between the 2 points, or in terms of probability of error. Thank you so much.